Hello and welcome to the second episode of AlgoSmash. Today we'll be covering a problem called permutation from the CSES set, and I'll leave a link to it in the description below so that you guys can also check the problem out, brainstorm a bit, and submit your solution to this problem. Let's jump right into the problem statement. It asks us to output a permutation of integers from 1 to n such that no adjacent elements have the absolute difference of 1. As usual with any problem, it will be much clearer if we go through a few cases. Now, if we look at the most trivial case when n equal to 1, there is only one permutation possible, which is the element 1. And since there is no adjacent element to compare it with, this is the solution when n equal to 1. 1 is the solution. If you look at the case when n equal to 2, there are two permutations possible. 1, 2 and 2, 1. And in both these cases, we see that the adjacent difference is 1. When you look at a slightly more complicated case where n equal to 3, there are 6 permutations possible because 3 factorial is 6. And if you look at each of those permutations one by one, we find that there is always a pair of adjacent elements whose absolute difference is 1. In the first case, it is 1, 2. In the second case, it is 3, 2. In the third case, it is the elements 2 and 1, the first positions, and so on. So every one of these cases, we are able to find two elements which are adjacent to each other having an absolute difference of 1. Hence, there is no solution when n equal to 3. Now, it's very easy at this point to abruptly conclude that for all n there is no solution and the solution exists when n equal to 1 only. But this would be a very wrong conclusion because there exists solution for higher n. For example, I suggest you guys pause the video and try to find a valid solution for n equal to 5. I assure you there exists a solution. I hope you guys did that. And a valid solution might be 2, 5, 3, 1, 4. Let's look at all the adjacent elements and see why this is true. 2 minus 5, the absolute difference of 2 and 5 is 3. The absolute difference between 5 and 3 is 2. 3 and 1 is 2. 1 and 4 is 3. So there is no pair of adjacent elements in this particular permutation which have the absolute difference as 1. Hence, it is a valid solution. A very good approach to these kind of problems can be to divide the problem set into even and odd sets. For example, in this case, when n equal to 5, the odd numbers that come into that range from 1 to n are 5, 3, 1, and the even numbers are 4 and 2. Now, a good thing to note is for all the elements belonging to the even set, the difference between the adjacent element is always going to be 2. For example, 2, 4, 6, 8, 10. These are all your even integers. Every even integer is the previous even integer plus 2. So the absolute difference between all the integers in the even set is going to be 2. Similar for the odd case. The absolute difference between any two adjacent elements belonging in either the even set or the odd set is going to be 2. So if we look at both of them separately, they don't violate our problem condition. You will never find adjacent elements with difference as 1 if we look at them separately. The only problem here is how are we going to combine these two sets in order to get a valid solution for n equal to 5. One way to do so might be, let's write all the odd integers like this, 5, 3, 1, and let's plug the even integers at the end, 4 and 2. Is this a valid solution? Yes, this is also a valid solution. The only thing to note is we are going to pay special emphasis to this. Why these two elements? Because 1 is the last element of the odd set in this case, and 4 is the first element of the even set. So as long, I'll call this a link. This is how we're linking those two even and odd sets together to form a solution. As long as the absolute difference between these link elements are greater than 1, or it should not be 1 basically. As long as the absolute difference between these link elements is not 1, we get a valid solution. Now let's see why this is. We know that the last element of the odd set is always going to be 1. No matter what n you take, when n is 7, when n is 9, when n is 10. If n is 10, you have odd integers as 9, 7, 5, 3 and 1. If n is 5, 5, 3, 1. If n is 11, 11, 9, then 7, 5, 3 and 1. You always know that the odd set ends with the integer 1. And you always know that the even set will start with an integer with an integer greater than 2 as long as the n in question is greater than 3. If n was 3, then the even integer set would start with 2. And why is that a problem? If instead of 4 there was 2 here and we are looking at the case where n equal to 3, that would be a problem because the absolute difference of 1 and 2 would then become 1, which would violate our condition. So the only thing we are noting is these link elements will always have an absolute difference greater than 1 because the last element of the odd set is 1 and the first element of the even set will always be greater than 2 as long as the given n is greater than 3. So this is the main takeaway for this problem, and just to make it absolutely clear, let's take a few examples, a few of them where n is odd and a few of them where n is even, to just drive the point home and there is no confusion for this. When n is, let's say, 10, let's write all the odd integers first. We have 9, 7, 5, 3 and 1. So far no problem. For the even integers, let's write that. All the even integers are 10, then we have 8, then we have 6, then we have 4, then we have 2. So if we look at this, this is the last element of the odd set and the first element of the even set is 10. These are our link elements again, and as usual the absolute difference is 9, which is of course not 1, and all the other elements here, as we see, have an absolute difference of 2. All the other elements have the absolute difference of 2. 10 and 8 also have the absolute difference of 2. So that is why we paid special emphasis to those two elements. Now let's look at n equal to 11. Let's take an odd example. When n equal to 11, let's first again write all the odd integers. 11, 9, 7, 5, 3 and 1. Again, look here. We always end the odd set with 1. And now let's write all the even integers. 10, then 8, then 6, 4, 2. As usual, you see here, the last element of the odd set is 1 and the first element of the even set is greater than 2. Is greater than 2 for all cases where n is greater than 3. Because when n equal to 3, the largest odd integer in that case, which is less than or equal to 3, will be 2, and 2 will be here, and 2 cannot be here next to 1 because that will violate our condition. So for all n greater than 3, no matter whether it's an even n or an odd n, this way of constructing a solution always works because the last element of the odd set is 1 and the first element of the even set is an even integer greater than 2. So I hope that that was clear. Now let's look at the code implementation. Okay, so here as you see, I first take n as input and I write my base condition. In my base condition, I check if n is less than or equal to 3 and n is not equal to 1. Because when n equal to 1, I know that there is a solution, the solution is 1. But if n is 2 and n is 3, I have no solution. For every higher n, I have a solution. Again, if you're still wondering why, it is because, as we see in the previous slide here, the first element of the even set has to be an even integer greater than 2. Only then there exists a valid solution. Okay, this is why. And for every n that is greater than 3, there exists a valid solution by this approach. Because I see a lot of people, when they see a pattern like this, they don't think. They just take it as a given that this pattern works. But the only way to truly understand is to justify or prove why this pattern works for all higher n, as I showed you in the previous slide. Now coming back to the code, the base case is fine. There is no solution for those cases. The else part. Now you might be wondering, what is this n plus n mod 2 minus 1? Basically, for any given n, I want to find out, for any given n, for example, let's say n equal to 10. I want to find out the largest odd integer less than or equal to n. Now a good way to think about this is, if I want to find out the largest odd integer that is less than or equal to given n, it can either be n itself if n is odd, or it can be a number 1 lesser than n. For example, when n equal to 10, the largest odd integer less than equal to 10 is 9. But if n was 9, the largest odd integer less than equal to 9 will be 9 itself. So I was just lazy to like find this out separately. So I thought this was an elegant approach where I first find out the remainder when n is, let's say, 10 here. So 10 is an even integer. Hence, when I divide it by 2, the remainder is 0. So for all even integers, this term will be 0. And hence, I find out the odd integer as n plus 0 minus 1. Because n minus 1 is the largest odd integer less than equal to the given n. Similarly, in the second for loop, I find out the largest even integer less than equal to given n, and I suggest you find out why this n minus n mod 2 works in the even case. I just find it to be like an elegant way to code instead of having a separate a variable to store the odd and even integers outside the for loop. But of course, that will increase the readability. So I guess that's a decision you have to make in the code. And let's see how this works. It's pretty straightforward. Let's take the example when n equal to 15. When n equal to 15, I basically first print out all the odd integers, that is 15, then 13, so till 1. As you see, I decrement the odd counter by 2 each time. Then I find out the largest even integer less than equal to n in a similar way, and in this case it is 14, and I print the even integer decrements of 2 until I reach 2. That's why I have even greater than 0. Normally I don't have even greater than equal to 0 because I have the permutation of integers from 1 to n. So I cannot include 0 there even though 0 is an even integer. That is why. So let's take another case where n equal to 8. Just so that this is absolutely clear. When n equal to 8, the first for loop, I have 7, 5, 3 and 1. This will be printed. In the second for loop, 8, 6, 4 and 2 will be printed. As you see, every adjacent pair of elements, if you see, the absolute difference is greater than 1, and nowhere will you find an adjacent a pair of elements whose difference is 1. Nowhere. So this is why this problem, this solution works, and I thought it was a pretty neat problem. You don't need any knowledge of data structures of anything of that sort, and you just need to apply your brain and find something that works, justify it, code it, and submit it. So that's it. Let me know how this was. Was it clear? Was it confusing? And let me know in the future what type of videos you want me to make. See ya. Adios.